Anyway, so let's start with our first lecture today. So it's my pleasure to welcome Tamas Gorbe, who will talk about classical integrable systems. Please, Tamas.
Thank you, Misha. Hello, everyone. So this is the first lecture. It's on classical integrability for finite dimensional Hamiltonian systems. And if you don't know any of these words in the title, I will tell you all about them. So let's move on. As Misha said, we will have 5 lectures, and I listed these lectures with the time of each lecture, time and date of each lecture, and the topics. So as you can see, we are going to go through various aspects of integrable systems. It's a broad area, so it has to do with classical mechanics, but also quantum mechanics. So Maxim will, in the second lecture, will tell you about quantum integrable systems. Then in the third lecture, we'll have Bart teaching us this very important method of coordinate beta ansatz. The fourth lecture, in the fourth lecture, we'll have Francesco, who is going to talk about integrable PDEs. So that is a continuous version of integrable systems. And in the last lecture, Mats will tell you about discrete integrable systems. So you see various aspects: classical, quantum, continuous, and discrete aspects of integrable systems. So let me just very roughly tell you what an integrable system is in general. It's something, a system, a physical system for which we can solve the equations of motion, basically, but it's a very rough description. I just listed a few things here. So I just, basically our aim is to solve these equations of motion, solve the dynamics of the system. And this can be done because there are many conserved quantities, many physical quantities that are conserved during the time evolution of the system. And well, I just included this top line that this is due to lots of hidden symmetries, where that's something that I really like about these systems, that in one sense or another, they might have lots of symmetries. So if you want to get a few examples, see a few examples of integrable systems, I would give you this list, which sounds, I think, really impressive, that the hydrogen atom is an integrable system. Certain equations of water waves are integrable. So you can see this little movie playing here, where you have water waves in a shallow channel maintaining their shape very nicely. So these are solitons, if you've ever heard these, this word soliton. So these are solitons interacting with each other. But they also appear in optical fibers. So there is a model of optical fibers where integrable systems come into play. And even in biology, we see integrable systems popping up. For example, in lipid membranes, you can see similar waves propagating. So this was just a rough description. Let me get to the actual content of the lecture. So we are going to work in this lecture within classical mechanics, and in particular the Hamiltonian mechanics, where the state of a system is described or specified by a set of generalized coordinates. So these are n real numbers that coordinate some sort of space, which I denote by C. So the number of these coordinates is called the number of degrees of freedom in the system. So how many of these real numbers you need to specify the configuration of your system. You can think of a simple pendulum where it would need only one such number to give you the configuration of the pendulum. That would be the angle that the pendulum makes with the vertical downward direction. But of course, it's not just the configuration that is needed, not just these generalized coordinates for a system. for the state of the system to be specified, but also so-called generalized momenta. So these are a generalization of the notion of the linear momentum of a particle or of a body. So this also lives in this collection of momenta also lives in Rn. So n real numbers put together in a n-tuple. So this is just the state of the system. It's a point in 2n dimensional space. What is driving the system, so what generates the dynamics of the system is this Hamiltonian function, which you could think of as the total energy of the system. It's just a function which assigns a number, the energy, to each state. So you take each state specified by this collection of Q's and P's, and the Hamiltonian assigns a real number to it, the energy of that state. I will not be very rigorous with these notions, but at certain points I might give you the more rigorous versions of these definitions. So for example, this Hamiltonian has to be a smooth function on this space of states. So this space of states is usually also referred to as the phase space. Okay, so we have the state of the system, we have the Hamiltonian function, the total energy of the system for each state, and then the way motion is generated is we have these equations of motion, Hamilton's equations, which you can see down here. So we have the time variable, and each of these coordinates and momenta will depend on time, and the equations of motion give you the time derivatives of these coordinates and momenta in terms of the partial derivatives of the Hamiltonian function. So you can see that these equations, this is a set of 2n equations if you have n degrees of freedom, and they are coupled ODEs. There is 2n of them, and you can see that they are almost symmetric. There is a bit of antisymmetry or asymmetry in this equation. Here in the first one, for the time derivative of the qj's, we have a plus sign in front of the partial derivative of h, and in front of the in the second line for the time derivatives of the jth momenta, we have a minus sign in front of the partial derivative of the Hamiltonian. Okay, so these are the equations, the differential equations that we have to solve if we want to calculate the future state of a system. Another way of saying what we have here is that the states evolve along the integral curves of the Hamiltonian vector field, which is denoted by x sub h, and it's put together from these partial derivatives of h. It's almost like the gradient of a function, but there is some sort of antisymmetry. And first I take the partial derivatives with respect to p, the components of p, and then I take the partial derivatives of h with respect to the components of q with a minus sign. So just to show you like an example, sort of picture that you could have in mind. So here's a very simple phase space, a very simple state of space. It's just 1 degrees of freedom. So there is only one q coordinate and only one p coordinate. So that's just the 2D plane of states. And you can imagine that you start from a point. So each point has a certain energy. You start from an initial point, and then you want to solve the dynamics generated by the Hamiltonian. And so the Hamiltonian vector field could look something like this. So I hope it's visible that we have all sorts of arrows pointing at each point of the phase space. We have an arrow pointing into some direction. So let's say that the initial state of our system is that point, and then all we have to do if we want to solve the dynamics or if we want to see how it evolves in time, this point, we just have to follow the arrows basically and see where we end up. So it might have something, dynamics like this, might be periodic. If we start up here and follow the arrows at each point, we might end up going from left to right. So there is all sorts of things that could happen. This is actually the Hamiltonian vector field of the pendulum, the simple pendulum. So back to the slides. So this is basically what a Hamiltonian system is, what classical mechanics is in terms of Hamiltonian functions and so on. To give you a specific example, I would like you to consider the Kepler problem. So this problem involves a point particle which has mass m moving in 3D space. So again, we have to have these generalized coordinates and momenta. Well, in this case, it is the actual coordinates of the point of this point particle moving in space. It has 3 coordinates, so 3 numbers, real numbers, to specify its configuration. So it has 3 degrees of freedom, and it can take any, it can be at any point except the origin. And the momenta has, again, 3 components, and it can be any 3D vector. And this is the linear momentum of the point particle. And it's attracted to the origin by Newtonian gravity. So that's the Kepler problem, where we have a point particle attracted to the origin according to the inverse square law. So the total energy of the system in this attractive gravitational potential would be, the total energy would consist of the kinetic energy, which is just the length of the momentum squared divided by twice the mass. So this is just 1/2 times m times v squared if you would use speed instead of momentum, minus the potential energy. So, but it's actually plus the potential energy. So the potential energy is negative. It's minus k over the length of q, length of our vector pointing from the origin to this point particle. So if you want to write it in components in the full form of the Hamiltonian, we would have the components of p squared and added together divided by 2m minus k over the square root of the squared sum of the coordinates. So this number k is a constant, it's a positive constant, and it's basically the term that is responsible for the attraction, for the strength of the attraction of the origin. So it involves the gravitational constant and so on. The Hamilton's equations read as follows. So it's just the usual. So the first set of equations is not surprising, because it just tells you that the velocity, the speed of each component is basically just pj over m. So it's just the linear momentum divided by the mass. And the time derivative of each component of the linear momentum is just minus k times qj over the length of q cubed. Okay, so you could write this in vector notation as well, and then you would recognize the sort of the inverse square law, because the time derivative of the momentum is basically the force, and you would see that there is the 1 over q squared, so the 1 over distance squared law appearing if you would write it in vector notation. So this is the example that I would like you to consider as the most, well, one of the most famous examples of Hamiltonian systems. And this is the example I'm going to come back to each time a new notion is introduced during this lecture. So what I would like to, let me just show you an animation of 2 point particles attracted to each other in in Newtonian gravity. So this motion or this dynamics actually can be reduced to the Kepler problem. So if we can solve the Kepler problem, we can solve the gravitational attraction of 2 point particles. So this is actually probably one of the first examples of integrable systems and a place where the equations of motion have been solved. This was, of course, solved by Newton some 350 years ago. So let's move on. Now we know that what a Hamiltonian system is. Now we need some sort of technical equipment, some sort of tools that we can work with. One such tool would be the Poisson bracket. So the Poisson bracket of two functions defined on this space of states, the phase space, is the following expression. So we have two functions, think of them as two physical quantities, and their Poisson bracket is another function, is a new function made out of these two by summing a certain combination of their partial derivatives. So what we do is we sum for j, with j going from 1 to n for all degrees of freedom. We are adding up the partial derivative of f with respect to the jth component of q times the partial derivative of g with respect to the jth component of p, then minus the partial of f with respect to pj and the partial derivative of g with respect to qj. So this is a very sort of, when you first see it, it's a weird looking beast, but this is a very handy tool in actually reformulating the equations of motion for any physical quantity, as you will see in a moment. So let's just go through a few examples. So if you would calculate the Poisson brackets of these components, so for example, qj and qk would have the Poisson bracket, just simply substitute for f, you would substitute qj, and for g, you would substitute qk. If you do that, you will quickly see that when you try to calculate the partial derivative of qk with respect to pj, you will get 0. Okay, so, and the same thing happens in the second term, where you try to calculate the partial derivative of q with respect to qj with respect to p, k or pj, you will get 0. So that's why this Poisson bracket is 0. And similarly, the second one, the Poisson bracket of the components of the momenta is also 0. Now, the only non-zero Poisson brackets of these generalized coordinates and momenta is when you take qj and pj. So this weird-looking symbol delta jk is just a shorthand for saying that this is 0 if j and k are different indices. So if, for example, if j is equal to 1 and k is equal to 2, then this is 0. But if j and k are equal to each other, then you get 1. So this is the Kronecker delta. And in fact, indeed, if you check, for example, the Poisson bracket of q1 and p1, you would get in this first term, in this first product of these partial derivatives, you would get 1, but all the rest would give you 0. So these are the so-called canonical Poisson brackets. And this bracket, this new tool that we just introduced, has various properties that are very useful. So it is bilinear, it is antisymmetric, it satisfies the so-called Jacobi identity, and it also knows the Leibniz rule. So let me just go back to my notebook and show you what these things mean. So, so it's bilinear, which means that if I take a linear combination of two functions, or a linear combination in the first component. It doesn't have to be two functions, it can be any number of functions. The point is that this can be broken into C1 times the Poisson bracket of F1 with G plus C2 times the Poisson bracket of F2 and G. Okay, so this is true for the Poisson bracket, and it could be also in the second slot. So it's bilinear, so it knows the same thing in the second slot. Let me just quickly write this out. So C1 and C2, they are just constants. They are just real numbers. So for any such linear combination of two functions, we would get D1 times the Poisson bracket of F and G1 plus D2 times the Poisson bracket of F and G2. Okay, so this is the bilinear property of the Poisson bracket. Next, we have an antisymmetry. So antisymmetric. So that just means that, and you can probably read this off of the definition. Let me see if I can go back. So if you just look at this definition, you can see that if you switch the order of F and G, you will get exactly the negative, the opposite sign from this relationship, because you have Qj and Pj here, and here you have Pj and Qj. If you swap G and F, you will get a overall minus sign. So if I just write that the Poisson bracket of G and F is minus the Poisson bracket of F and G. So there's this antisymmetry in this bracket. Now the Jacobi identity is something that you might have seen before. If you know about the cross product of 3D vectors, you've seen something like this before. So the Jacobi identity of the Poisson bracket is just you take three arbitrary functions. I will call them F1, F2, and F3. I take the Poisson bracket of F1 and F2 and consider the Poisson bracket of this bracket with F3, a third function. Okay, and if I do this in a cyclic permutation, so what I'll do next, I'll go for the Poisson bracket of F2 and F3 and take the bracket of that with F1, and then again shift the indices in a cycle once more to consider the Poisson bracket of F3 and F1 and take the bracket of that with F2. Now I have three terms, and for any three functions, this expression will give you 0. So that's the Jacobi identity. So the Poisson bracket knows this for any three functions. Next, we have, well, the last property is the Leibniz rule. So actually this Jacobi identity is something that you can check. So if you just use the definition, by definition, this is something that can be checked. And actually, if you want, it's a good exercise to check if you understand what this Poisson bracket is. And for the last property that I have here is the Leibniz rule, which might not tell you much, but it's actually telling you that this Poisson bracket kind of behaves as a derivation. So taking the Poisson bracket of functions with another given function behaves like derivation in the following sense. So if I take the Poisson bracket of G1 times G2 with f, with the function f, this can be written as the Poisson bracket of f and G1 times G2 plus the Poisson bracket of f and G2 times G1. Okay, so you can see what happens here. We have a product of two functions. Poisson, taken the Poisson bracket of that with f is like taking the Poisson bracket of the first factor, then multiplying it by the second factor, and then taking the Poisson bracket of f with the second factor and multiplying it with by the first factor. So that's like the derivation of a product, differentiation of the product of two functions. So now let me go back. We now know what these four properties are, and using these properties, one can actually derive the equations of motion for any quantity, any physical quantity f. It can be quickly summarized as this. So let me just really quickly derive this to you for you. So I have a function f, and I take the time derivative of that function. So just by using the chain rule, so this is a function of 2n variables. There are these q's from q1 to qn, and the p's from p1 to pn. So if I want to write the time derivative of such a function, I should sum for every index, j going from 1 to n, and write this as the partial derivative of f with respect to, let's say, qj times the derivative of qj with respect to time. So this is just the chain rule. And similarly for the components of p. So if I want to save space, I would just do as follows. I would just add to this the partial derivatives of f with respect to pj, and of course the time derivative of pj with respect to the time derivative of pj. So this is what I'm summing, and what you can notice that here we have the time derivative. Well, here we have the time derivative of qj and the time derivative of pj, for which we have Hamilton's equations. So if we apply, well, if we use Hamilton's equations, what we'll get is the partial of f with respect to qj, and then remember the time derivative of qj is just the Hamiltonian function, the partial derivative of the Hamiltonian function with respect to pj, and next we have, in the other term, we have the partial derivative of f with respect to pj, and then we have the time derivative of pj, which according to Hamilton's equations should be minus the partial derivative of h, the Hamiltonian function, with respect to qj. So there's a minus sign. That's why I didn't write anything. So this is just a minus sign. And now if we look back at the definition of the Poisson bracket, you can see that this expression, what we have here, is nothing but the Poisson bracket of f and h, the Hamiltonian function. Okay, so I was assuming that this quantity f does not depend on time explicitly. If it would depend on t as well, there would be the partial derivative of f with respect to time added to this expression. But the point is that the equations of motion, the time evolution of any quantity, can be expressed by using this Poisson bracket. So that's very handy, because now we can basically say that if f and h, this physical quantity f, Poisson commutes with the Hamiltonian, meaning that their Poisson bracket is 0, then we can say that the time derivative of f is 0, meaning that this quantity f is constant in time. It doesn't change as time evolves. So what we have is f being a constant of motion, as we say. And actually the reverse is also true. So if we would take f instead of h as our Hamiltonian, since there is a certain symmetry in this Poisson bracket, it would be also true that the Hamiltonian function would be constant along the integral curves of the Hamiltonian vector field associated to this quantity f, so xf. Okay, now let's see an example. But before I look at this example, let me just quickly go back to this to the notepad. So what it means, what it really means to have Poisson commuting functions is that if we have this phase space and we take an initial point, we take a point, state, an initial state in this phase space, and take our Hamiltonian function, and just we did at the beginning of the lecture, we let it evolve for, let's say, t1 for some time to get to a new state, and then we would introduce a new Hamiltonian function that Poisson commutes with our original one, and would now take this point and let it evolve through some time t2. This would be another time parameter to get to another point. So this is our initial state. This is our final state. The point is that first we went with our Hamiltonian, and then we switched to another Hamiltonian function that commutes with the initial one. If we would do it in the reverse order, so first we would evolve, use the time evolution to evolve for time t2 to a state, and then from that point we would use the first Hamiltonian to let it evolve that state for time t1. We would end up in the same point, in the same state. So that is what we mean when we say that these flows are commuting. So these are the flows which take points of the phase space and let them evolve for some time. Let me go back to the slides. So as I said, there is this example of the Kepler problem for which we have many constants of motion. So of course, the most well, obvious one probably is the energy, is the total energy of the system. So the sum of the kinetic and potential energies is constant throughout the time evolution. So whatever value you fix it at, it will stay at that value while this point particle is moving. Now another conserved quantity is the vector of the angular momentum, which is just the cross product of q and p, these vectors. And that is conserved because this potential is central, meaning that the attractive force, the force which acts on this point particle, depends only on the distance from the origin. Actually, it always points towards the origin or away from the origin if it would be a repulsive force. So that's the point, that it's always pointing to the center. And for all central potentials, the angular momentum is conserved. Now, finally, there is this third conserved quantity, which is very special to the Kepler problem. It's called the Laplace-Runge-Lenz vector. It's the cross product of the linear momentum with the linear momentum with the angular momentum minus m times k times the unit vector that you get by dividing q, the position vector, by its length. Okay, so if you count these up, so this is a scalar quantity, so that's just one conserved quantity, but these other two quantities are vector quantities with 3 components each. So if you add these up, 1 plus 3 gives you 7 conserved quantities, which actually is too many in the sense that we only have 3 degrees of freedom. So if and our phase space, the space of states is double, its dimension is double that, so it's 6-dimensional. We have P1, P2, P3, and Q1, Q2, Q3. So that's 6 real numbers, and we have 7 conserved quantities. It would actually be impossible to have this many consort quantities that are all independent of each other. And as it turns out, there is only 5 of them that are independent because, for example, the Runge length vector is perpendicular, it's orthogonal to the angular momentum. And the total energy of the function, the Hamiltonian function, can be expressed using the Runge length vector and the angular momentum. So, and these two constraints cause these 7 consort quantities to boil down to 5 independent ones. But what is really interesting is for the moment is that there are 3 quantities. We can pick 3 quantities out of these 7 that pairwise Poisson commute, or as we also say, which are in involution. So that means that the Hamiltonian Poisson commutes with the squared length of the angular momentum, but it also Poisson commutes with any component of the angular momentum, of course. But let's pick the 3rd one. And of course, the squared length of the angular momentum would also Poisson commute with its 3rd component. So we have 3 quantities, H, L3, and the squared length of L, which are all Poisson commute in a pairwise fashion. So that is leading us to this notion of integrability. Okay, so let me now finally define what I mean by a classical integrable system. So a Hamiltonian system, such as we've seen in the previous slides, with n degrees of freedom, is called Liouville integrable if there exist functions h1 to hn, so we have n functions, such that they pairwise Poisson commute. So the Poisson bracket of hj with hk is 0 for all indices j and k running from 1 to n. And they must be functionally independent. So these functions, these quantities really have to be independent of each other. And finally, of course, the main Hamiltonian, the main total energy function of the system should be expressible using these Poisson commuting functions, h1 to hn. Quite often, what we have is actually the Hamiltonian being the first of these n quantities. So the reason that these systems, these Liouville integrable systems, are very special and indeed are important examples of Hamiltonian systems is that for these systems we have something called the Liouville-Arnold theorem, which says that if we fix the values of these quantities h1 to hn at some, we fix them at some generic values c1 to cn. So these are just some generic values that we fix them at. So we take a point in the phase space, a state where these values are generic. And then we consider those points, all of those points in the space of states where these functions take those values. So in other words, we take this level set of in the phase space, the level set of those points Q and P, where Hj of Q and P is Cj for all indices j going from 1 to n. What turns out to be the case is that this level set is invariant under the Hamiltonian flow of the system. So you can imagine something that I've drawn before. So we have this time evolution, the system evolves in time, but this level set is not going to change. Okay, the points on the level set might wander around, but the set as a whole will not change its shape. And in fact, if this level set MC is compact and connected, then it can be shown that it is diffeomorphic to an n-dimensional torus Tn, which is parameterized by these angles phi1 to phi n. So this level set, if it's compact and connected, it's like a torus, you know, like a donut shape, with these angles phi1 to phi n, parameterizing it. And it turns out that these angles evolve linearly in time, meaning that the time derivative of these phi j's are constant. Okay, and the point of this theorem, the really important point of this theorem, is that this allows us to solve the equations of motion. So one can introduce new coordinates, new coordinates in this space of states, in which the equations of motion are easy to solve. And this is only possible because we have a integrable system, because we have this very nice structure for this system with many conserved quantities, and actually even even stronger condition here. Okay. Now, of course, one could ask, are there systems which are even better than integrable? And the answer is yes. And you've already seen this a very important example of such a system. But let me just say that these systems that are even better than integrable, we call them super integrable. And they are just integrable systems which have additional constants of motion, so additional conserved quantities. I call them f1 to fm, so there is m of them. And the point is that these functions, f1 to fm, Poisson commute with hj, but only up to the first n minus m of them. Okay, so they don't Poisson commute with every quantity hj, but only the first n minus m of them. And they are also functionally independent of the previous quantities. So the f's are independent of the h's. And there is the very special case when we have as many of these extra, these additional constants of motion as possible. So that is n minus 1. So remember that we have this, we have the degrees of freedom being n. So the dimension of our phase space is 2n, meaning that if you fix 2n independent functions, you would just freeze the dynamics. That would give you a point in the phase space which just couldn't move because it's so constrained that there is no way for it to move. So if you just take one less of these quantities, so 2n minus 1, meaning that we have these n quantities h1 to hn, and then we have n minus 1 of them, of these additional quantities, f1 to fn minus 1, then we have something that's called a maximally superintegrable system. And this is something that you've already seen. So there is an example of such a system, and that is of course the Kepler problem. So the Kepler problem has in fact 3 degrees of freedom, and 2 times 3 minus 1, that is 5 of these independent independent conserved quantities. 3 of them are in involution. So the Kepler problem is maximally superintegrable. It's not just integrable, but it is maximally superintegrable, and that's the reason for it being so nice and so easy, well, relatively easy to solve. Okay, let me just show you. Actually, this is something I wanted to also show. Is this Rungelenz vector? So this is, of course, an example of a Kepler ellipse. So there is the origin, and this is the ellipse or elliptical orbit that this point particle would trace. And the point is that if we have the angular momentum that is perpendicular to this plane, so sticking out of this plane, then then the cross product of the linear momentum and the angular momentum will again be lying in this plane. And if you take that cross product and subtract off m times k times the unit vector, unit position vector, you will always end up with a vector that is the Runge-Lenz vector, A, which is always constant, so it doesn't change. These are 4 instances of this vector A, which actually always points to this apex of the ellipse, and it's kind of proportional to the eccentricity of the ellipse. So I mean the length of it. So going back to the slides, now we can ask, and I think there was a question in the chat asking about these concert quantities, how to find them, how to generate them. And so that's a very good question. That's a natural question. Once we know that these integrable systems are so nice, that's good, but how do we find these concert quantities? And that is what this slide is about. It tells us that there is a different way of formulating these equations of motion. So, and this is called the Lex representation, which is the Lex representation of a finite dimensional Hamiltonian system is a pair of matrices L and M, which depend on these coordinates Q and P. So it's not just constant matrices. These are matrix valued functions on the phase space, such that if you take the time derivative of L, which means that taking the time derivative of each entry of this Lex matrix L, that is equal to the commutator of L and M, if and only if the equations of motions are satisfied. So you remember Hamilton's equations, but this is just reformulating that. So basically what we say that we have this Lux representation if this equation is equivalent to Hamilton's equations. Again, this bracket of L and M here is the commutator, so it's just L times M minus M times L. And if we have such a representation, we can start generating explicitly concert quantities. So we can generate concert quantities in an explicit form. Namely, what we have is that this matrix L will, of course, evolve in time. So each entry evolves in time. But the point is that the eigenvalues of this matrix are constant, so they don't change while the clock is ticking, you know, while time evolves. The eigenvalues of this matrix won't change. And one way to see it is that to say that the traces of powers of the Lex matrix L are constant. So this is just a small exercise that, again, I encourage you to go through. To calculate the time derivative of the trace of some power of L that is equal to, well, let's call the power the exponent k, that is equal to k times the trace of L to the power k minus 1 times the time derivative of L, which by this Lux equation is equal to, the time derivative is equal to the commutator. So if you write that as L times M minus M times L and use the linear property of the trace and also the cyclic property of the trace, you will find that this is indeed 0. So that was the time derivative of the trace of some power of L. And it was actually, I did not specify the exponent because it can be any exponent. So since these traces of powers of L are constant, that means the characteristic polynomial of L is constant, and the roots of which would be the eigenvalues of our matrix. So what I should point out at this point, that this only gives us quantities that are conserved, so that are constants of motion, but it doesn't necessarily mean that they will all Poisson commute. But in what I should also note here is that in most examples, the interesting examples that we usually see, it actually produces these quantities h1 to hn, which all Poisson commute and gives rise to an integrable system. So just to give you an example of such a Lax representation, again, I'm using the Kepler problem. So it has a slightly involved Lax representation, 2 by 2 matrices. So these are just 2 by 2 matrices where we have the Qj's and Pj's appearing in the components in the entries of L. And the point is that there are these auxiliary variables. These are can be thought of as complex numbers. And the point is that if you take this equation, time derivative of L is equal to the commutator of L and M. And for the off-diagonal entries, the second component of the first row or the first component of the second row, you just expand around the poles, these lambda j, you will see the equations of motion appearing in these expansions. And L, as I said on the previous slide, can be used to generate the conserved quantities. So for example, the components of the angular momentum can be generated using the trace of L squared. So you square the Lax matrix, take the trace of it, and for example, considering such an expression, will give you the first component of the angular momentum squared. Okay, so this is how you generate these conserved quantities. And I think my time is up. So with this, I would like to thank you all for listening, and I'm ready for questions if you have any.